Hi, I'm Ji Yan, and in this talk I'm pleased to present a recent work done with my colleagues Nathan Krombers, Jocelyn Busson, Yassine Rouachek, Thomas Krajnik, and Li Sun, on developing a quantifiable stratification method for tidy-up in-service robotics. The world today faces many challenges such as population aging and labor shortage. Service robots are expected to be a powerful helper for human society in addressing these challenges, and many application scenarios can be imagined, including various home services, healthcare, public cleaning, etc. Tidying up is a typical task for service robots, in which the robot needs to sort cluttered objects as required, usually by category at specified locations. This task seamlessly integrates the autonomous navigation with autonomous manipulation, hence is very challenging. Specifically, it covers many aspects of robotics including semantic mapping, object detection and manipulation, decision-making, navigation and obstacle avoidance, and so forth. One of the key issues in completing such a task is how to continuously select the object to grasp and take it to the delivery area, especially when the robot works in constrained and partially observable environments. This usually involves many aspects of robot decision-making, such as strategy design, integration, runtime selection, hypotheses, performance, etc. Motivation for our work can be seen in World Robot Challenge 2018 partner Robot Challenge Real Space, where a Toyota HSR robot was asked to put 10 scattered toys in order on the toy shelf in a children's room in 12 minutes. For such a complex problem, we contend that an effective way is to use simple methods to minimize the impact on future uncertainties, and this simplicity is better to be quantifiable. Also, keeping the competition and industrial applications in mind, the developed method needs to be process controllable. Our approach, named OFSM, based on the well-known philosophical thought and the classic computer science method, has several features that make it well suited for the tidy-up task. First, it grades the plan by explicitly counting the number of actions that the robot needs to perform, and holds a priori assumption that the uncertainty is proportional to this number. Second, it responds to changes and uncertainties in the environment through repeatable actions, that is, facing many changes with no change. Third, it is close to human intuition rather than relying on complex models to solve the problem, especially when the environment is constrained and partially observed. We explicitly design and formally describe the test cases, that are expected to constitute a benchmark bridging the competition and the research. Through scenario planning and simulation experiments, we illustrate the effectiveness of our approach. In order to clarify the research problem and elicit our approach, we divide the problem into 4 subcategories from simple to complex, including fully observable, fully reachable, partially observable, fully reachable, and partially observable, partially reachable. The observability and reachability covers both object and deposit. Our focus in this paper is on the most challenging category, partially observable, partially reachable. For the sake of system-wide clarity, our prerequisites include a. The robot has a wheeled moving basis rather than legs and it is not allowed to move over any objects on the ground. b. The robot has a pre-built environment map about the static objects such as walls and stationary furniture. And c. The robot knows the 3D pose of the deposits with the corresponding categories, and each object must has a corresponding deposit. Our approach is based on the theory of Occam's razor, which is formulated here. Where A indicates the number of executable actions, O is the known observations of the robot, and P represents the motion plan in a set of considered plans. Specifically, AP is related to the design of the plan and can be regarded as a priori, while AOP depends on the current observations of the robot and can be regarded as a posteriori. The idea is to find the plan P that requires the minimum number of actions, which is then considered as the best one, as less complicated plans are less likely to fail. Moreover, minimizing also implies minimizing the impact on the environment, thereby minimizing the uncertainty of the future environment state. A deterministic finite-state machine is then integrated, in which the output depends on both input and system state. The machine can be formally defined as a sextuple, where in the context of tidy-up, S is a finite set of states which represents the overall mission. S0 is an initial state which can be considered as the state before the robot entered the room. O is the input which includes both known and unknown observations. A is the output which contains robot actions on the environment. T is a transition function. And F is the set of final states including the completion of the tidy-up task. For a better illustration, we give 3 instance plans from simple to complex. The first plan, denoted by P1, is based on a greedy algorithm, which empowers the robot to always grasp the closest object I. The second plan, denoted by P2, is based on the shortest path, from the robot position to the object position, and then to the deposit position, which can be used when P1 is not feasible. The third plan, denoted by P3, can be selected when neither P1 nor P2 is feasible. As an example strategy for system unlocking, in P3, the robot is asked to remove one or more objects starting from the closest one and put them in a suitable place, until getting a feasible object delivery solution. Empirically, that suitable place could be the nearest past waypoint but neither used for grasping nor for delivery. The actions taken into account for our instance plans are listed here in order to reflect the observance of the Occam theory, namely the fewer the actions, the simpler the solution. The state transition table of the instance plans is also shown in this slide. To illustrate the effectiveness of our method, we explicitly designed 3 test cases, with the real robot and the competition scenario kept in mind. As tidyup is a complex and multi-module coordination and integration demand task, we first explain the relevant premises, assumptions, and system parameters, that can be severed for future benchmarking on the specific module, then present the scenario planning and simulation experiments. So here we list some related settings. Here are some figures to help us better understand the experimental settings. As can be seen from the upper left, an X-Shan RGBD camera on top of the robot is used for object detection. But due to its effective working distance and field of view, sometimes it is tricky for the robot to get the knowledge of the entire environment. The upper right shows the competition arena specifications of the World Robot Challenge 2020, which is a room contains a variety of furniture, and one side of it is set as the delivery area, while the rest of the area is for scattered objects. The lower part of the slide shows the 3 test cases we designed. The square-colored areas represent the deposit location, while the colored circles represent different objects. Different colors indicate different categories. R stands for robot. As you can see, there is an unobservable and unreachable object in case 1, an unobservable and unreachable deposit in case 2, and both in case 3. This video played at 20 times speed shows our simulation experiment with test case 1. The 2 tables here show the results of scenario planning and simulation experiments. For the former, we count the number of times each plan is used and the total actions required to complete the entire task. For the convenience of calculation, we count 4 actions if the robot completes P2. Empirically, fewer actions usually mean faster completion of tasks. It can be seen that by using our method, the tidy-up task can be completed within a limited number of actions, while without the need for complete and global awareness of the environment. For the simulation, we record the time required for the robot to complete the overall mission and the total distance traveled. As you just saw from the video, we omitted the process of object recognition, grasping and releasing in order to focus more on the evaluation of the decision-making part. In case 1, using greedy algorithm and using OFSM get the same result as only P1 was performed in OFSM. In cases 2 and 3, only using greedy algorithm caused the task to fail. Okay, time for conclusion. In this paper, we proposed a quantifiable stratification method for tidy-up task with service robots that are typically domestic mobile manipulators. Called OFSM, it reintegrates traditional approaches into modern applications, which includes a series of independent action plans, from simple to complex, to cope with ever-changing object deposit configurations. Different from the existing work, the core idea of our proposal is to always prioritize the simplest method that inherently has the least impact on future uncertainty, while the effectiveness has been illustrated with well-designed test cases. The future work will take dynamic objects such as humans and other robots into account in the task planning, for human-aware navigation or manipulation. Moreover, we will consider integrating the lifelong learning of spatio-temporal representations that allows the robot perform the right action at the right time through active navigation. I hope you enjoyed this talk. For more information, please check out our paper. Thanks for listening.